This is an easy concept to talk about and is highly useful when we deal with functions. Why is that? Well, when you call a function, you'll need to remember the current state of the main module or the calling module, meaning where you are in the code, the values associated with each of the in-scope variables, and the return address you need to come back to once you have completed the execution of the function. Stacks are used to store this information. A stack has two operations, pushing in and popping out.
Yeah, and when a program runs, both code and data are loaded into memory. The code refers to the area where the instructions for the program are located. The code segment contains all the compiled executable code for the program. Write permission to the segment is disabled here, as the code by itself really does not contain any variables and therefore has no need to write over itself. But by having the read-only and execute attributes, the code can be shared between different copies of the program that are executing simultaneously. So the next section refers to the data, initialized and or uninitialized, required by the running of the code instructions. The data segment contains all the global data for the program. A read-write attribute is given, as programs would change the global variables. There is no execute attribute set, as global variables are not usually meant for execution.
Picture the stack as a single-ended data structure with first in, last out data ordering. This means that when two or more objects or elements are pushed onto the stack, to retrieve the first element, the subsequent ones have to be popped off the stack. In other words, the most recent element remains on top of the stack. As shown previously, there is a progression from a lower memory address to a higher memory address as one moves down the stack.
You'll probably be surprised to learn that stack-based buffer overflows have been very common exploitable programming errors in software applications. Very simple things can be used to attack. A stack overflow occurs when data is written past a buffer in the stack space. Remember, it overflows. And the behavior of the program could be unpredictable, or there could be a compromise in terms of the actual data. These issues have been highlighted for years, as you know, and the attacks have been becoming less prevalent, which is good news. However, they are still important to learn about and warrant continuous focus on the identification of potential vulnerabilities in the future.
That's correct. Over 100 functions within libc have security implications.
Wow.
Can you imagine? Over 100. The impact could vary from trivial to catastrophic. The simple function printf can give remote admin access to an attacker if not handled programmatically.
Wow.
Larger variables, when assigned to variables that are small, could overwrite controlled data and data in adjoining items. This could potentially change the return address and lead to malicious code being executed. If it gets there, that's it.
Yeah.
You have the attacker doing his job. As we are aware, when functions are invoked, stacks store the parameter details. What if the variables get a lengthier value than what it should ideally have? It could result in a stack overflow.
Recursion is a major area where you need to be very, very careful. You will need to know how deep you can go for just those reasons. If you keep on calling recursively, the stack may get filled and you will end up having a stack overflow error. You also have to ensure that there is a way out from recursion. There should be a terminating condition, always. The overflow can overwrite the return pointer so that the flow of control can switch to malicious code. C language and its derivatives have many ways to put more data than anticipated into a buffer.